Hello everyone, in this video we will talk about permutations. So in some cases when we're trying to define the sample space, it is difficult to identify how many sample points we have in the sample space. So permutations and combinations are helpful tools to find or to compute the number of sample points in the sample space. So pretty much we will cover permutation, some rules for multiplication. In the upcoming videos we will see cells and combinations. So the first rule is the multiplication rule. So if an operation can be performed in one ways, this is the number of possibilities in which you can perform an operation, and if there is a second operation in the process and that second operation can be performed in two ways, then when we add them together and we try to compute the number of different configurations or possibilities given the rule of multiplication, is going to be n1 times n2 ways. So we multiply the number of ways in which we can perform the first operation times the number of ways in which we can perform the second operation. So this is an example. If in experiment of tossing two dice the number of sample points is n1, this is for the first one, and n2 for the second die, then given the rule of multiplication, in total there are 6 times 6, that's equal to 36 different sample points. This rule of multiplication is useful when we are trying to buy a product, and you can configure different features of the product, such as the color, some sort of capacity. Then you just multiply the number of ways in which you can select each of the features, and the total is just the multiplication. So let's see more examples of the rule of multiplication. A developer of a new subdivision offers prospective home buyers a choice of Tudor, rustic, colonial, and traditional exterior styling. Ranch, two-story, and split level are the floor plans. So there are two features of the house here: the exterior style and the floor plan. Then the question is, how many ways can a buyer order one of these homes? Since there are two features, exterior style and the floor plan, so let's check how many options we have in each. So for the exterior style, there are 4 alternatives: Tudor, rustic, colonial, and traditional. Now in regard to the floor plan, there are 3 options: ranch, two-story, and split level. Now if we want to use then the rule of multiplication to find how many possible house configurations we have here, is just the multiplication of the 2 features. So that will be the 4, given that there are 4 options for the exterior style, times, for the floor plan, there are 3 alternatives. So in total there are 12 possibilities or 12 configurations. These 3 here help us to visualize all those 12 configurations, right? So for each exterior style we have 3 floor plans. So for Tudor there are 3, for rustic there are 3, for colonial there are 3, traditional there are 3. So in total we have 12 different configurations. So far we have used the rule of multiplication only when we have 2 features, but it is possible to have multiple operations or multiple features. So if that's the case, then we will use the general multiplication rule. So if we have k operations and each operation can be performed in different ways, then the total number of possibilities is going to be given by the multiplication of n1 times n2 up to nk, where nk refers to a number of ways in which we can perform operation k. So let's read this example. Sam is going to assemble a computer by himself. He has the choice of chips from 2 brands. So chips, the type of chips, that's one feature, and it has 2 alternatives, 2 options: a hard drive from 4, memory from 3, and an accessory bundle from 5 local stores. So in how many different ways can Sam order the parts? So since there are 1, 2, 3, 4 different features, and each feature has a different number of possibilities, right? 2, 4, 3, and 5. Then the total number of configuration given the rule of multiplication is just the multiplication of the number of alternatives per part of the computer. Therefore, using the rule of multiplication, we multiply these alternatives and we get that in total there are 120 configurations. If you want to use this idea when you're configuring, let's say, a Dell computer or any other brand, I'm pretty sure that you will find way more different configurations, because you can change the color of the product, the capacity of the RAM memory, or the hard disk drive too. So there are even more features that you can modify, and of course that will increase the number of configurations. Okay, so now let's introduce a permutation. A permutation is just an arrangement of objects where the order matters. The order is important. So if I switch the position of an object, then I'm getting a different solution. So in general, if you want to arrange n different objects, then the number of ways in which we can arrange those objects, it's n factorial. Why? Because in the first one we can place n objects, right? But if we don't have repetition, then in the second position we will be able to arrange n minus 1, and then in the third position n minus 2. Why n minus 1? Because we have already a position 1 object in the first one. Then for the third position n minus 2, so we keep going until we have finished with the arrangement of the products or the items. Therefore, in total, this is n factorial. N factorial is giving us the number of permutation of these different n objects. So the number of permutation of different objects, that's without repetition, that's n factorial. But if repetition is allowed, then the number of permutations is going to be n to the power of n. So why we have that difference between n factorial and n to the power of n? Because again, with a repetition, so we can locate n objects in the first position, n minus 1 in the second position means that you cannot allocate the same object that is in the first position, right? So that's because this is without repetition, n minus 2. But in this scenario, and we keep going here, but in the second scenario, if repetition is allowed, then we can place n objects in the first position. Since repetition is allowed, then n objects in the second position. Same thing until the last position. So that's why we get the n to the power of n. So let's check an example, a couple of examples here. So in how many possible ways can 6 people be seated in a row? So we have 6 positions in the row, position 1, 2, 3, 4, 5, and 6. And since we have only 6 people, that means without repetition, right? We cannot place the same person twice in the same row. Therefore, in the first position, we can place any of them. So there are 6 alternatives. But since we have already placed one here in the first position, then for the second position there will be only 5 alternatives. 4, 3, 2, and 1. Rule of multiplication, that's how we get the 6 factorial right there, which is equal to 720. Okay, let's now check this example, and let's consider 2 scenarios, without replacement and with replacement and repetition. So in how many possible ways can letters A, B, and C be arranged? So we have 3 items that we want to arrange. So without replacement, so the number of options is just 3 factorial, right? There are 3 alternatives in the first position, 2 alternatives for the second position, and only 1 is left, right? That's equal to 6. But now, if we allow repetitions here in this problem, then in every single position we have 3 possible letters, right? So that will be 3 times 3 times 3, or 3 to the power of 3. That's why the equation is n to the power of n. And of course that will increase the total number of sample points in the case where we have repetition. So it's 27 compared to only 6 when repetitions are not allowed. There are some special cases of permutation. So far, we have been assuming that we are going to arrange the n different objects. But in some cases, you don't need to arrange all of them, only a subset of those n objects. So let's say we have 100 objects and we're gonna take 4 of them. Then that's a special case of permutation. So in general, if n distinct objects we take r, then the number of ways in which we can arrange those r objects is given by the following equation. Please notice this notation. That means that from the n objects we permute only r. R is the subset that we take. So the number, the total number of points that we might get, it's n factorial divided by n minus r factorial. N, total number of objects. R, it's how many objects we're going to select. Again, r is smaller than n in this special case. Okay, so let's check this example. In 1 year, 3 awards, the Research, Teaching, and Service Award, will be given to a class of 25 graduate students in a statistics department. If each student can receive at most 1 award, so that means that the same student cannot get 2 awards, only 1 at most. Only 1 at most. So how many possible selections are there? So this is a typical example where we have n objects, right? The 25 graduate students, but we're gonna pick only 3, right? Because there are only three awards, 3 positions: research, teaching, and service. So how many possible selections are there? So we can use this equation, right? So from the 25 students, we're gonna permute, right, a selection of 3, the 3 positions. So using the equation, that will be 25 factorial divided by 25. R means the number of selection of selected, so that's 3, right? There are 3 positions, factorial. So that's 25 factorial divided by 22 factorial. This is equal to 25 times 24 times 23, right? That will be the solution. 25 times 24 times 23. That's using the equation, right, that we just covered. Now, if you want to understand better why we have 25 times 25, 24 times 23, it's the same as, okay, there are 3 positions, right? Research, teaching, and service. Those are the 3 awards. So for the research, let's say that there are 25 possible students that might get the award. Remember that if one student, let's say, gets the research award, then for that student it's impossible to get the second award. That was a condition here because they will get at most 1 award. That means 0 or 1, but it's not possible to get 2. Therefore, for the teaching award, there will be only 24 candidates left, right? And then for the service award, there will be only 23 students that might get that award. So we get the same result, right? 25 times 24 times 23. So either way, using the equation or just this logic, you will get to the same answer. Now, imagine that there are no constraints here. Imagine that a single student, if the student is good enough, then that student might get the 3 awards: research, teaching, and service. So if that's a possibility, then we're allowing for repetition. So if that happens, then we might have 25 students that might get the research award. But if repetitions are allowed, then we still have 25 students that might get the teaching award and 25 students that might get the service award, because here we allow repetition. Then of course the number of possibilities or points is going to be higher, right? That's 25 times 25 times 25. All right, so let's check this example. In this problem, the president and a treasurer are to be chosen from a student club consisting of 50 people. So how many choices of officers are possible if A, there are no restrictions. So let's solve each of those questions. Okay, here. All right, the first one. There are no constraints. So we have in total n individuals, right? 50 students, we may assume. And there are two positions. So we're gonna they want to elect the president and the treasurer. There are two positions. So that might be considered as r equal to 2, right? It's like the subset of individuals that are gonna be selected in this problem. Okay, in part A, then if there are no restrictions, so how many different choices of officers are possible? That's the first question. So we will use just the question that we just discussed. So from the 50, we're gonna permute two positions. So that's 50 factorial divided by, this is 50 minus 2 and the result factorial. So this is 50 times 49. Or remember, if the first position, let's say, is the president, then there are 50 students. Since it doesn't make sense that the same student will be the president and the treasurer, then for the second position, the treasurer, there are 49. So it's the same thing, 50 times 49. 50 times 49. That will be the answer of the first part. So if you find the number of 50 times 49, that will be 450. All right. Now for part B, the question is, A will serve only if he is the president. A means a specific student. You can call him Arthur if you want, like specific name. So that person will serve only if that person is elected as president. Otherwise, the person won't serve. Therefore, that means that that person is not going to be elected as treasurer. All right. So if that's the case, then the number of configurations in which A, or that specific person is going to be a president, it's 1 times 49. So what is the meaning of 1 times 49? This is person A is selected as president, so that's only one option, right? Times there are 49 left that can be elected as treasurer. So that's one alternative. But there is a second scenario here. Remember that A is not interested in being elected as treasurer. So if A is not elected at all, then the number of possibilities will be, there are 49 students that might serve as president. That's from here I will remove student A, and of course A won't be included also as treasurer. Therefore there are 48 possible students. Then the total number of points is equal to 49 plus 2,352 2,352. So that's for a total that's equal to 2,401. All right. Again, this B, it's when A will serve only as president. So the first part accounts for when A is a president, and the second part, it's accounting for when A is not elected at all. So that's when all the students are president and treasurer, but A is not included in that selection for the second part. Okay, now in C, B and C will serve together or not at all. That means that B and C are two specific students, they are good friends, So they will serve only if they are elected together, or they won't serve. That means that B doesn't want to serve just by himself. Same thing with C. They want to be together. Alright, so first, let's find the scenarios where they are together. I'm gonna try to be like to split the expression in a, like in very small parts. So this is when B is president and when C is treasurer, right? But then we might have the opposite scenario, right? When C is the president and then B is the treasurer. We have two options so far. This is 1 times 1 plus 1 times 1. This is 2. But then we need to account for those scenarios where they are not elected, right? When none of them, because they won't serve if they are not together. Therefore, that will be, there are 48 students left for president, and of course, for treasurer, there will be 47. This is equivalent, guys, as 48 permutation 2. Remember the special case. From 48 objects, we're going to permute 2. We're going to take 2, right, for the permutations. So this is equal to 2258. Alright, now let's check the last one. The last one is D and E will not serve together. D and E will not serve together. It looks like they're enemies, right? They don't like each other. They don't get well along. So they won't serve together. Maybe they won't be a good team if they work together. So let's find how to get the number of possibilities here. Alright, so in part D, there are two options. There are two people that won't be serving together. So let's check that. So maybe D will be elected, right? But if D is selected, E won't be elected. Or maybe E is going to be elected. That means that D won't be elected. Or they won't be elected at all. So let's check those three scenarios, right? The first one, when D is selected, D might be elected as president or even as treasurer, right? So this is 1 times 48. That means that D is president and someone else is a treasurer, but that someone else does not include, of course, student E, because they don't get along well. We have the alternative solution where someone else is president and D is the treasurer, right? So these two scenarios account for the cases where D is elected. But now we have the same case for E, when E is elected. So maybe E will be the president and someone else is going to be the treasurer, or someone else is the treasurer and E is the, someone else is the president and E is the treasurer. So those are the 4 scenarios or 4 possibilities when they are elected but not together, right? And of course, we need to include the case here where they don't get elected at all. So that will be 48 times 47. This is equivalent, as you know, 48 permutation 2. Guys, I highly encourage you to start checking on your calculators. You will see this notation like NPR or NCR. That's for permutations and combinations, and that's where it's an important operation that you need to start checking on your calculators to make sure that you master and you know how to use them. Alright, that means that in total there are 2,448 points or alternatives in which D and E won't serve together or won't serve at all. Now there is a shorter alternative here. There is a possible solution that it's simple. That's like, let's assume in how many ways they will serve together. So there are only 2 ways. D is president, E treasurer, or the other way around. E president and the treasurer. So there are only two ways in which they are going to serve together, right? So we know that in total, without restriction, there are 2,450 points. That's without restriction. Therefore, the alternative solution is take all the possibilities, 2,450 minus the two alternatives where they serve together, and of course you will get the same number, right? The 2,448. This is an alternative solution, the easy one, but of course I wanted to show you first the long path, because I think that you will learn more of that from that road. Okay, there are two more special cases to cover. The circular permutation, that's when we don't have a linear arrangement. This is when we are arrange objects or individuals in a circular arrangement. Imagine that you have like a circular table and you want to sit people in these different positions, right? So how many different points or configurations you will find. In order to do so, the circular arrangement has this number of possibilities, n minus 1 factorial. So it's slightly different than the linear arrangement where it's n factorial. Here it's n minus 1 factorial. Therefore, in this example, it says that Gracie, Jennifer, and Brian and Umberto, 4 people, they are going to be seated in a row. So if that happens, then the number of arrangements is 4 factorial, right? As we just covered in the previous slides. But now if we have the same people, but we want to sit them in a circular table, then it's n minus 1 factorial, right? So the solution will change a little bit, right? It's going to be 3 factorial. So from 4 factorial in the linear arrangement, and the circular is going to be 3 factorial. That's 6 possible configurations. Okay, this is the last special case that we're going to cover. This is when we have object types. So far we have assumed that the n objects or individuals that we want to arrange in the permutation, they are different. All of them are different. But in some cases, we may have some repeated objects or objects of the same kind. The typical example of this is, imagine that you are trying to arrange some books, but you have you have one book like with several copies, like the same book, exactly the same book several times. So this is this case, because if you switch 2 of those books that are the same, then you have the same solution. So we need to remove those arrangements where you are just switching equal objects. So in order to do so, the question here for the general case is that, okay, if you have n objects and you have k different objects, from each of those k objects you have different, like multiple number of the same type, then you need to divide the n factorial over the number of objects that you have of the same of type number 1 factorial times the number of objects that you have of type 2 factorial up to the number of objects that you have of type k factorial. Alright, now using this logic, let's solve the next example. So it says that in a college football training session, the defensive coordinator needs to have 10 players standing in a row. Among these 10 players, there are 1 freshman, 2 sophomores, 4 juniors, and 3 seniors. So how many ways can be arranged in a row if only their class level will be distinguished? If the class level will be distinguished, only a class level, that means that here we have several objects of the same kind, because we have 2 sophomores, we have 4 juniors students, and 3 senior students. So we have individuals of the same kind. Then we need to remove some of the arrangements where we're only switching positions between objects of the same, or individuals in this case, of the same kind. Then if you use the equation, the number of permutations is going to be 10 factorial, because there are 10 positions in total, 10 individuals, right? And now we need to divide it over the total number of individuals that we have of the same kind. So for freshmen, there is only 1, that's 1 factorial, times sophomore, there are 2 sophomores, times 4 juniors factorial, and times 3 juniors factorial. That means that in total there are 100, this is 12,600 possible arrangements. And of course, if we do not consider their year or the class level, imagine that we consider all of them as individual as different individuals, then of course the number of arrangements is going to increase because we're not going to remove, or we're going to divide it by the n1 factorial up to nk factorial. If we don't consider the class level and we just consider them as different people, then the number of arrangements is going to be 10 factorial, as that's the equation that we were using before. Alright, so this is how we use permutations. We have covered some of the special cases. Remember that this is an important tool to be able to quantify the number of sample points in different problems. Please remember that in permutation, the order matters. The order matters. Okay guys, I'll see you in the next video.